Hello, welcome back to the course. In this section, I will talk about finite state machine. Finite state machine is a useful architecture to describe a sequence of predefined events, actions, or states. So let's take the vending machine for example. Vending machine is a machine that will sell goods to customers. So for the vending machine, there is usually predefined events it can occur. For example, it usually goes through the following states. Start. That may be one customer clicks the start button on the touch screen. Then it will go to the select product stage. That is, customer can select the product he wants on the touch screen. Then the customer may press the OK button on the touch screen and the machine goes to the insert cash or coin stage. Yes, that is ask the customer to insert money to the machine. So in this state, customer will insert money to the machine. After the machine detects that there is enough money for that good, so its state will go to the pop out goods stage. That is, the machine will give the goods to the customer, then will give exchange if there is any. At last, the machine will go to the end stage. That is, the whole process of this settlement is ended, and after the end, it will go to the start stage, wait for next customer to buy something. So this may be the predefined stage or state you can occur at the vending machine. For the control of vending machine, we can use a finite state machine to design it. And also, there is predefined state for some bus protocols, such as FPGA XI interface. What is FPGA XI? I will introduce them several chapters later. So, for the vending machine, the transition of the state may be something like that. Yes? Okay. For state machine, there is basically two types of finite state machine. The mini type, that is, the output depends on the current state and its inputs. And the Morse type, that is, the outputs only depend on the current state. So let me show you the figure. Okay, this should be the This should be the mini type. Yes, output depends on the current state and the input. So this register, or you can say this register. There may be several registers here. This register is a state. It will remember the state. Yes, which state you are now. This register will remember which state you are now. And the output will relate to the current state and the input value. So this is mini style finite state machine. And this is a more types FSM. The output is only related to the current states. Okay, from the figure you can see there is about 3 parts in this logic. That is the state register, yes, and the state transition logic. That is, you use the current value of state and the input signals to calculate the next state, to calculate the value of next state. So you have the state register, the state transition logic, and the output logic. Yes, you may use the state value and the input to calculate the output of the finite state machine. Okay. Okay, if you think this is hard to understand, I will give you some example later. So the key points of FSM design is defining the state you have to use. Yes, define a state. That is, you have to define how many states you will use in this design. Such as for the vending machine, we have defined 1, 2, 3, 4, 5, 6 states. Okay, this is the first key point for design. The second key point for design is you have to define the transition flow. Yes, this is the arrows. The transition flow of each state and the transaction condition. That is, under what condition this state machine will translate from this state to this state. What's the condition? You have to think out it before coding. And what's the condition for a state to loop back to itself? Yeah, that is, for cycle 1 is in this state, and for cycle 2 is still in this state. Yeah, what's the condition? And what's the condition for a state to transmit from this state to the insert money state? Yeah, what's the condition? You have to define it, or you have to think about it before coding. Okay, this is the 2 key points when you want to define a finite state machine. And for the vending machine case, the state defined here may not be very good. Okay, you can add some new states if you need it. For example, if the customer has inserted some money, but finally he found that he doesn't have enough money to buy that goods, what he will do? So one solution is the machine eat all the money the customer has inserted. Okay, so it can change to this. Yes, so you can change to this stage and end. But I think you must think this is a bad solution. And the third solution may be, after some time, the customer found it, he doesn't have enough money, he may choose the cancel. Yes, the machine may provide a cancel button in the touch screen. Then the customer may press the cancel button and the state transition may be go to here. Yes, just return back all the money has inserted and skip the pop out stage. Then return back the money and okay. So this may be a good solution for this situation. So the choose of states and the transmission of states It's depend on the function. Okay. Okay, let's have an example. If we want to define a function of sequence detectors, for example, the sequence is 1 0 1 1. This is the first bit. This is the last bit. Okay. These bits will be serial input from the input pin D in, which will input 1 bit data for every cycle. When the input sequence matches 1 0 1 1, the output signal match will give a 1T pulse, 1T high pass, and it will be 1 cycle later. Yeah, will be 1 cycle later than the detection of sequence. And we have an enable signal for the D in. We just check the value of D in when En is high. So for this figure, we assume En is always high. Yes. So you can say this is an example. 1011 gives 1T pulse high and match. Then there is some overlap. Yeah, overlap between each group. So this is 1011 and gives 1 cycle high pass unmatched. So the spec enable the overlap between groups. So how to define the final state machine for this function? Yeah, just take out your pens and papers and draw something like that. Yes, and you can add your condition here. Yeah, you can add your condition. Yes, you can add your condition at this point. Okay, just try it, and I will go on with my lecture. So this is an example design from me. I designed 4 states. That is the idle, the first one, then 1 with 0 and 1 0 1 state. This is transition conditions. When we receive a 1, change to this state, and also you need to check the value of enable. Okay, that is if En equal to 1 and D in equal to 1, it will transmit from idle state to S_1 state. So if the input is still 1, so it will stay and this state for many cycles. So if it receives at 0, it will transmit to this state. Then receive and 1 will translate to this state. At this state, if it receives and 0, yeah, that is, yes. So it will translate to this state. Yes. And if it receives at 1, it will generate the match output and translate to this state. Yes, this state may be the first bit of next group. Okay. So this is the coding. After the design of the states and the state transmission conditions, we have to code it. Okay, let me show you the code. Okay, you can see there is something new for you. The parameter. Parameter is a Verilog keyword. It will define some symbols with a fixed value, such as in this module, the S underline idle symbol will be treated as 0 of 2-bit width. The S underline 10 symbol, okay, will be treated as 2 of 2 bits width. Yes, that is the same as you write Nice. Yes. But using the symbol, the code may be more meaningful. Yes. And the code will be easy to understand. Okay, let's take a look at the code. For the first always block. The first always block is a sequential block, yes. So you just code the function of the state register. Yeah, this signal state equal to the Q output of the register, and this signal next state equal to the D pin, yes, of this registers equal to the D pin. This is the signal value on the D pin, and the next always block will describe the state transmission logic. Yes, it will use the state value, the value in the state register, and some input to calculate the value of next state. And this is a combination logic. So end state is the signal on this point. So if you have defined this the state transmission condition, the coding will be very simple. Okay. For example, the state will just change, or the state will just transmit when the En is high, and for idle state, it will change to S1 when Din is high. Yes. And for S1 state, this is transition. And there is no need for you to write the else. Yes. Yeah, there is no need for you to write these two lines, as we have the default value. Yes, we have assigned the default value for end state. And this state, the value of state must be equal to S1. Yes. Then For this state, the code for this state, when receive 1, when receive 0. Yes. Then code for this state. Okay. The third orange block that is used to generate the output. The output of the FSM. That is the match signal. So the function is when En is high and the state is in this state, and we check the D is 1. Next cycle, we will output match. And we will clear it in next cycle. So make sure. So this will make sure the whites of match is just 1 cycle length. Okay, this is the coding of this design. Generally, you see 3 always blocks. Yes. 1 always block defines the state registers. 1 always block, a big always block defines the state transition logic. And the last always block defines the output logic. For this part, it must be sequential logic always block, and this must be combination logic always block. And for this block, okay, in the figure, it's combination logic, but in the reference code, this is sequential logic. You can understand it as we have AND 1 register. Yeah, we have AND 1 register. After this, output combination logic. So for the third always block, combination logic or sequential logic, both are okay. Okay. Okay, and we call this coding style. Coding the finite state machine in 3 always blocks. We call this coding style 3-block style. 3-block style. Okay, please try to code this simple example at your own location.